Okay, our final lesson of this unit is solving exponential and logarithmic equations. Exponential equations are equations in which variable expressions occur as exponents. The results below is useful for solving certain exponential equations. So anytime we have a variable in our exponent spot, we call it an exponential equation. And this can be useful that when we have the same base, so whatever our base is, base of b, if b equals 3, 3 and 3. If b equals 5, 5 and 5. If and only if x equals y. So if we look at this example, if 3 to the x equals 3 to the 5th, then x equals 5, because it's going to be 3 to the 5th equals 3 to the 5th. Now, that's obviously a super basic, simple explanation. So we might have a slightly more complicated problem. Let's say we have something that looks like this. 4 to the x equals 1/2 x minus to the x minus 3 power. The first thing I'm going to do is I'm going to rewrite my base numbers so that I can have the same, I want them to be the same number. So I'm going to rewrite 4 as 2 squared. And I'm going to rewrite 1/2 as 2 to the negative 1 because, again, a negative exponent, we move to our denominator. So we're going to say that this is 2 squared to the x equals 2 to the negative 1 x minus 3. Well, now we can go ahead and simplify again. An exponent raised to another exponent means we multiply. So 2 times x is 2x. Negative 1 times x is negative x. And negative 1 times negative 3 is positive 3. Again, using this power right here, I say, hey, I have the same bases, which means if I want them to equal each other, my exponents are going to have to equal each other too. So I'm going to say 2x equals negative x plus 3. Add an x, 3x equals 3, therefore x equals 1. So let's check our solution. Again, it's always good to check your answer. Taking my original equation, I'm going to plug in a 1 here and a 1 here and get 4 to the first equals 1/2. 1 minus 3 is negative 2. So 4 equals 1/2 to the negative 2 is like saying 1 over 2 squared, which is 1 over 1/4. A fraction of a fraction is really keep, change, flip. So we do, in fact, get an answer of 4 equals 4. So this solution checks out. Another way that you can work to solve equations is by taking a logarithm of each side. So let's say that we are trying to solve 4 to the x equals 11. Now, we probably don't know off the top of our head what this x value is. This is not one of those problems that we've, learned and memorized. So what we're going to do is we're going to take our original equation and we're going to take the log base 4 on each side. So I'm going to have log base 4 of 4 to the x equals log base 4 of 11. Again, anything I do on the left side, I can also do on the right side. Now, if you remember one property that we've discussed, when you have a base of the same number, it's going to cancel out. So that's going to help me simplify because now I just have x on this side, log base 4 of 11. But we may want to simplify this, and we learned last lesson that we have a change of base formula where we can turn it into the common log with a base of 10. So again, log base 10, I don't need to write that. Log base 10 of 11 and log base 10 of 4. So I can use my calculator to plug these in, log of 11 divided by log of 4, and we're going to get x is approximately 1.73. So again, if I were to plug that in, 4 to the 1.73 power, that is going to get me really, really close to 11. An important law that uses exponential equations like this is Newton's law of cooling. So hopefully you have heard of Isaac Newton by this point. This law states that for a cooling substance with initial temperature, so initial temperature of T sub 0, the temperature T after T minutes can be modeled by T equals T sub 0 minus T sub R e to the negative RT plus T sub R. I want to clean this one up a little bit. So let's just go through and label. Okay, so this is our temperature. This is our initial temperature. T sub R is our surrounding temperature. You know what E is. R is the cooling rate. That didn't work. Cooling rate. And then T stands for time. Lowercase t stands for time. And again, T sub R is the surrounding temperature. One more time. All right, so you are driving on a hot day when your car overheats and stop running. It overheats at 280 degrees and can be driven again at 230. Here, let me take a picture of this situation. All right. All right, so if we take our equation and we're going to plug in our values. So we know that we can drive again at 230 degrees. I started at 280 and it is 80 degrees outside. So that's my surrounding temperature. E to the negative, it looks like R is 0.0048. And then again, T is what we're trying to figure out. We don't know what T is. And then we have the surrounding temperature of 80 again. So again, just plugging in what I know. Keep in mind, our goal is to solve for T. So as I go through and start to simplify, I'm going to subtract 80 on both sides. So subtracting 80 minus 80 minus 80, I get 150 equals 280 minus 80 is 200 e to the negative 0.0048 t. Now we're going to get rid of this 200 by dividing both sides by 200. And we're going to get 0.75 equals e to the negative 0.0048 t. Again, t. So now that I want to cancel out this e, again, how do we cancel out e? We use the natural log. So I'm going to take the natural log of 0.75 and I'm going to take the natural log of e to the negative 0.0048 t, knowing that this is going to cancel out. So we only have the natural log of negative 0.75, or natural log of 0.75 is equal to this right here. And so now we're almost done. We can divide, because again, our goal is to get t by itself. Divide both sides by negative 0.48 divide by negative 0.48. And so we should get approximately 60 for t. So you would have to wait, according to this situation, you would have to wait about 60 minutes before you could continue driving. And just like how we talked about right here, we can use this type of idea, the property of equality for exponential functions. The cool thing is it basically works exactly the same for logarithms too. So we kind of have the same type of idea where again, if I know what my base is to an x and I know that it equals log base 2 of 7, well then x is going to equal 7. X has to equal 7. So we'll do an example of that. Solve log of 5 to the 4x minus 7 equals log of 5 to the x plus 5. Now I'm going to say, all right, the property of equality tells me that because I have the same base, or I have log base 5, I can compare the other parts because I know that that's already the same. So again, I'm trying to determine what is this going to equal. Subtract x, 3x minus 7 equals 5, add 7, 3x equals 12, and divide by 3, therefore x equals 4. Again, if I were to plug this answer in, I could plug this in all the way into my original, and I could double check to make sure that I get the same answer, which I will. We may have to exponentiate each side to solve it. So let's take a look at what that would look like. So let's take the example, solve log of 4 to the 5x minus 1 equals 3. So what I'm going to do in order to cancel out this log is I'm going to raise everything to this exponent. So I'm going to create a base of 4, but I'm going to bring up everything else right here. But remember, anything I do on the left side, I also have to do on the right side. So I'm raising all of this stuff up into my exponent and then bringing in a base of 4. And the reason I want to do that is because this cancels out. So we are only left with 5x minus 1 equals 4 to the third. We can simplify 4 to the third to equal 64. And now it's just 5x add 1 is 65. Divide by 5 and x equals 13. So I can use this exponentiation to help me simplify again when I don't have a log of 10. I like having a base of 10. If I get anything else, I usually have to do extra steps. Okay, let's see here. 2 more examples. How about that? First one, what is or are the solutions to log 2x plus log x minus 5 equals 2? For starters, I'm going to use the product property, and I'm going to smush these two together. I'm going to smush these two together because they're the same base. So I'm going to say I have log of 2x, and then I need to multiply it by everything inside equals 2. And then I'm going to exponentiate each side to get rid of my log. So again, I'm going to raise everything up to the log, and I have 2x, x minus 5 equals 10. squared. I have to do it on both sides. So this is nice because this cancels out. So I have 2x, x minus 5 equals 100. 2x squared minus 10x equals 100. Subtract 100, we get 2x squared minus 10x minus 100 equals 0. I would suggest dividing or factoring out, I guess if we just divide each side by 2. So again, I'm going to divide by 2 and divide by 2. So I'm left with x squared minus 5x minus 20. Anything divided by 0 is still 0. If I think about my factoring x, what two numbers multiply to get negative 20 but add to get negative 5? The only way that you can do that... Oh, Mr. Larson, this is not a 20. This is a 50. What two numbers multiply to get negative 50 but add to get negative 5? That's going to be a negative 10 and a positive 5. So my answer is going to be x minus 10, x plus 5, which again means that my actual solutions are x equals 10 and or x equals negative 5. But now we have to check that these work. So if I plug these in, if I plug in each answer to my original equation, when I plug in a 10 and I simplify, again, log 2 times 10 plus log 10 minus 5 equals 2. When I go down and simplify, I get log of 20 plus log of 5 equals 2, which means really I can get log of 100 equals 2. And in fact, log of 100 does equal 2. So 10 is a solution. However, when I try that with my negative 5, again, log of 2 times negative 5 plus log negative 5 minus 5 equals 2, log negative 10 plus log negative 10 equals 2. Log of negative 10 does not exist. So I really can't find anything because, again, it's outside of my bounds. It's not going to work. So I have to, if I get more than one solution, I have to check my answer to see if it makes sense. So algebraically, yes, I got two answers. But in the context of this problem, log of negative 10 is not defined. So negative 5 cannot be a solution. You could potentially even graph that. And again, if you graphed it, you would get something that looked like this. Here's your log function. And then here is when at x equals 10 and y equals 2. So again, if this is 1 and this is 2, this point right here would be x equals 10, and this would be your only solution. X equals negative 5 is all the way over here, and obviously your graph does not touch that.